Aloha, we are going over the second part of chapter one of our econometrics textbook, Intermediate Statistics and Applied Regression Analysis by Dr. Keith Criddle. So this is a lecture where I talk about multivariate descriptive statistics. Multivariate means you're looking at more than one variable that are combined. And we talked about the problem statement, identify the problem assignment. In this lecture, we'll focus on four different things. We'll look at the covariance, correlation coefficient. We'll talk about doing some hypothesis testing about the correlation coefficient, but that the same principle we talk about pertain to other types of hypothesis testing. We'll also discuss confidence intervals. Now, first of all, what is a covariance? It's how variables X and Y vary together. And there are a couple of formulas. Look at it for the population and sample. They have different symbols, and these are the annotation. As we can see, we're looking at the observation minus the average or the mu. We're talking about population. Population uses mu. If it's a sample size, we're looking at X bar or Y bar. But you look at the difference from a variable minus its average, and you multiply it by the same thing for the other variable, and then you take the product of those two and you average them together, and that gives you the covariance. The sample covariance is fairly similar, but you're looking at the sample means. And then there's something of a penalty when you're calculating the average, so 1 over n minus 1. And there's a couple of Excel formulas. Excel recently came out with some newer formulas than what the textbook has, which are a little bit simpler to use, not much. I think the other one was like covar, and then you have the two arrays. But with the newer formulas, you can do covariance.p and then put in the two arrays. Sample variance, instead of p, use s, same thing. And the way you interpret this is you look at if it's negative, then they move oppositely from each other. If it's around zero, then it's a linear relationship. It doesn't mean they're not related. It probably does, but it means there's no linear relationship. If you have a nonlinear relationship between the two, that could be manifest with the covariance of zero. If the covariance value is positive, then they do move together. Let's look at some data. I've got a data set over here, and I went to our world in data. I looked at GDP per meat capita, per meat consumption, and then I added a column adding all the meat together because it just has other meat, sheep, beef, buffalo, pig meat. I don't know why they don't call it pork. That's okay. Poultry. And then I just summed it all together. The total meat consumption per capita for people in the Philippines. And often we first get a data set. It can be useful to do some exploratory analysis. I'm going to select the data, click on Insert. I'm going to add a line graph. Let's see. I'll go to the x-axis, add year. So now we see that there's something of a positive relationship. I guess you can. Oh, how Garamond. You can adjust it however you want. I don't know. Sometimes maybe I spend too much time tweaking these graphs. I spend a lot of time fixing things, or just go with the default. I guess if you do exploratory analysis, that doesn't matter so much. You generally see 1960 till about, what is it, 1985, it didn't change very much. Since then, it's been growing. It's been increasing. And there might be a bunch of reasons for this. It might pertain to things like supply chain issues, maybe with their economy, or who knows. Let's look at GDP per capita. I'm going to do the same thing. Actually, you know what? I'll make it easy. I'm going to copy this chart. Instead of column G, I'll look at column H. I'm going to replace all of those. Let's see what GDP per capita has been doing in the Philippines. Looks like it's been same sort of a slump, but then increasing. So maybe there is something of a relationship between the two. Well, we can look at, let's look at the two. So instead of using A as the axis, right, I'm going to put G see if there's a relationship between I'm going to put these total meat consumption, insert, and then GDP per capita. So as money increases, GDP per capita increases, how much is the minimum? Let's go with 3,000. And then we'll do, there we go. It looks like that there's something of a positive relationship between GDP per capita and meat consumption. And so I think that can give us an idea as to what we might be able to anticipate with our graph. Okay, so I did some exploratory analysis. I've looked at things. Now I've got an idea of what to maybe think about. We're using our function wherein we have the average of x minus the average, y minus the average. Let's go ahead and plug those into our table, and we can hand calculate our covariance, how they relate to each other. X minus mu, and so I'm just going to say equal. We'll make that meat, and you can have one be meat, the other be GDP. You can swap them, but you still get the same conclusion. So that observation minus average of G, that's and then I'm going to copy that all the way down. And I'll do the same thing for GDP per capita. Of course, it's going to be negative at first, and then it'll be positive. They've been increasing. We have that positive relationship. Then let's take the product of those two. I times J. I'll copy that all the way down. And now we can calculate the covariance, which is average of what we have there. We've got this value 12,834.4. That works. We could also do, let's see, equals rho var. That's the older formula, this one that you found in the textbook. And that'll give you the exact same thing. Those numbers don't differ from each other. If you wanted to use covariance E, and you'll find that that the result will be the same. So we have 1283.38 instead of the formula itself. So we've got all these fancy formulas in here, or we just use the covariance. Now, I like to keep things a little bit more simple. Plus, if you did all your calculations right, they should be the same. But it's easy to do a computational mistake. And so for that reason, to make things more efficient, I try to use as many formulas as possible. Let's look at some of these things. Let's look at the covariance between sheep and goat and beef and buffalo. Covariance. Let's see, sheep and buffalo. And pork. And we've got some values on here. What does that tell us? It's positive, so we must have beef, buffalo, sheep. Oh, I did it. I'm one off. Beef and buffalo, sheep and goat. Let's make this C. There we go. Oh, that's almost 0. So it's not going to matter very much. I'm just going to anchor these right here. I can copy these over. Pork, that's more, but these numbers aren't really scaled, so it's kind of hard to tell what exactly they mean. So let's see. Make sure I got these right. I'm keep seeing by one. beef and buffalo. Okay, and then it's easier if we anchor these. And then like we copy and paste that and go back. So let's look at pig meat, pork and poultry. And really with this, we could tell that it's variance dot. We tell that it's positive, but it's not really scaled to anything, so it makes it hard to tell if it's a strong correlation. And so to do that, it makes sense to use a correlation coefficient, which is a scale-free measure. And so, you'll notice that, so here we have the covariance. We have the covariance in the numerator. We have to kind of annotate. We have the covariance in the numerator here. And then we have the standard deviation of X and the standard deviation of Y, which I guess is manifest right here. So once we, that's what we use for the population. Use the sample work coefficients. You use the same thing instead of the population, you use the sample. And the way we interpret this, the result is going to be somewhere between -1 and +1. -1 means you have perfectly negative correlation. +1 is perfectly positive correlation. 0 means they're not related. There isn't a linear relationship, or we say no correlation. Really what we mean is there's no linear relationship between the two. And I found this table, the size of correlation, and I don't know if it's official or not, but intuitively it sort of makes sense. And so I included it on here. And the formula we use is equals Correl, or correlation. So let's start plugging this in. It'll make a little bit more sense. Actually, let's do the calculation. If we look at it's, we need to get, we have the numerator already. Numerator is just the covariance. And let's go ahead and calculate the standard deviation. So to do that, we're going to do equals that things. There's two ways you can do squared. You can do that times itself, or you can just take that, the caret 2. I'm going to copy these all the way down. And we want to get the square root of the average of the formula that we had of that. And the second one we wanted for M. Yeah, the next thing that is from. And so when I do the calculation, it's the covariance divided by, and then we want to do both for standard deviations. That times that. And that gives us this correlation coefficient. We could also do Correl, which is the Excel formula, and we can let it do all the subcalculations for us all in a hurry. And you will notice if we did it right, we'll get the same value for both. And that makes more sense. So it's a fairly strong correlation between total meat per capita consumption and GDP per capita. That informs us that meat is a normal good. And you'll recall in your principles in economics class, normal good, when income increases, people buy more. By definitions that we got. Let's look at the correlation between the different types of meats. Or else, so I can get it right this time. Sheep and goat, beef and buffalo. Good. We'll copy this over. And so there's correlation. So let's go back to this 0.5. We're looking at moderate positive correlation. And it is possible it can be negative. That's not what we have here, but those are possible outcomes that we have. It looks like sheep and goats and pig meat are a lot stronger. Let's look at the Correl formula. It's a fairly strong correlation. I'm going to anchor these. F4 will anchor that. And then the last one is pork and poultry. Which has a fairly strong correlation. So when people are eating more pork, they're also eating more chicken. With more pig meat, they're eating more poultry, if you want to say it, as is described in the data. All right, well, that's what we have for meats and meats. Let's look at a couple of in the Philippines. But let's look at movies. A lot of us like movies. There's this data set that comes from the source, and it has a bunch of values. I wanted to add a couple of things. I went to, I think it was the St. Louis Bank, one of the Federal Reserve places, and I grabbed the CPI because as it makes sense, in my mind, it makes sense if we're comparing things from different years, you want to adjust for inflation. So I'm going to go to the CPI and we're adjusting for inflation. So we're looking at cell, let's see, B114. To do that, B114 divided by that year, CPI. I'm going to copy that all the way down. What this tells us is 1913, $1, $1 in 2025 is the same as $32.50 in 1913. I'm going to go to another year. $1 in 2025 is about $2 in 1997. That's how long it takes to double, at least using the rates of inflation. I'm going to come back in here to where it says Warner Brothers, and we have these movies were released at different dates, column K, and so I'm going to put in this adjustment value. VLOOKUP. It's a year, the release date, and we're looking at the CPI, third column. You can put false, we put 0, which means false. It's just easier for me to type. And so that means since 1933, $1 back then is equal to 25. Oh, did I get that backwards earlier? $1 in 1933 is the same thing as about almost $25 today. I'm going to copy this all the way down. A couple of these dates just has a year. And so I'll just adjust those formulas. Looking at the year, it's already the year. We already get formulated. So that's the CPI adjustment factor. So for gross earnings to make it $25, I'm going to hit that, multiply it by the multiply it by US gross earnings. And so in real dollars for this movie, the US the gross receipts were 57 million. It was 2.3 million back then, 57 million. So I'm going to copy this all the way over. Now we've got a little more data to work with. And let's look at a couple of things. What is the correlation between US gross tickets versus the budget to produce the movie? Looking at nominal. Correlation between budget. It doesn't matter the order we do things in. Budget. Okay, so it looks like it's sort of strong, moderately strong, 0.69, moderately positive correlation. That's what we're looking at. And let's do that for, how about if we adjust it for inflation? Those tickets. Last one's budget. Budget. Let's see. Look, it's the same correlation between the two. Well, that's because they're just adjusted for inflation. Okay, what happens if we look at US growth, world growth. How does Rotten Tomatoes, IDMB ratings, IDMB votes, how do these compare with each other? If we let's look at nominal, first of all, Rotten Tomatoes versus the US growth. Rotten Tomatoes rating equals Corel. World growth, Corel. Anchor these. And budget. What this is telling us is how do these relate? Does Rotten Tomato ratings, does that relate to the US growth? Barely. About world growth, maybe even less. The Rotten Tomato rating, the rating that they have, it relates to the budget. So that means if you spend more money, if you have a higher budget, are you going to get a better Rotten Tomato rating? Not. Looks like the relationship's not exactly linear. Same thing with IDMB ratings, and it's kind of weak with, but it's there for the vote. Looks like voting matters a lot more than the ratings do. I see the same thing for inflation adjusted values. We'll look at the US growth tickets, which are right here. I'm going to anchor these. And the easy way to copy a formula, you copy this. And I'm going to change this to H. Make that one more down. And this one is J. And I can copy these over. Oh, let me see. Okay, looks like I have a slight mistake in my code, what I typed. I need to get rid of. It's the anchors. Let's see. This is referring to the CPI for that year. I'm going to fix this. Now we have accurize the data a little bit. And we can look at the correlation. Okay, now we see that the correlation is not the same for if when it's adjusted for inflation. Well, now we have the formulas corrected. I anchored the row as well as the column, and I needed to just do the column. So that's been fixed now. So we have the real US gross budget a little bit lower. If we look at the real values, the things like for the budget compared to Rotten Tomatoes or IDMB ratings, it's pretty much nothing. There's very little correlation. There does seem to be the greatest linear correlation between the votes and how much money that gets put in there. That's a lot. Maybe their ratings don't work nearly as well as the votes do. I guess that's the conclusion I come to when I look at that. That's our correlation coefficient. It's great. Let's look at hypothesis testing. Hypothesis testing it's a very scientific approach. It's different from religion. If if there's a religious truth, somebody with the comprehension of an 8-year-old can know that is true. One can know that they are a child of God. One can, at 8, with an understanding of an 8-year-old, they can know for certain that Jesus is the Christ, that Joseph Smith was the prophet. All these things we can ask Heavenly Father, He'll give us an answer, and we know it's because those truths are absolute. That's different from science. Science has a completely different objective, which the reason why they can be very compatible is that, or incompatible, I guess, however you look at it, is that they have different objective functions. With science, with truth, you find the absolutes. With science, you go with the best thing until something better comes along. And it's still very powerful. In the 1960s, we put it, or whenever that was, we put a person on the moon with a plum pudding model. Since then, we've come up with much better ways to describe our, the physics. And well, we can do a lot more with it too. Just because something better might come along doesn't have to keep us from moving forward. When you do a hypothesis test, you have a null hypothesis, something that has the status quo, and you're checking to see if something better, if you either reject the null or fail to reject the null, alternative hypothesis. You use a bunch of different signs. With the null hypothesis, you use equal, less than equal to, or greater than or equal to. Alternative hypothesis, you tend to see not equal, less than, or greater than. You don't have the equality portions that you look at is in the null hypothesis. And there's a couple formulas. You can do a 1-tail or 2-tail. And when you're running a model, failure to reject the null means you don't have enough evidence. It's not necessarily proof that the model is useless. It just means you don't have enough evidence to reject it. If you reject the null, it means you have enough evidence against the null. So it better depends on the context and model specification. Let's look at, you can make it, there are different types of errors you can make. Type 1 error, type 2 error. Type 1 is a false positive, type 2 is a false negative. But the way you interpret this, I've put a table on the right that shows different correlation coefficients. And what happens if you vary the population size from pretty big to really small? So you calculate the t-statistics, and if you have 221, the 2-tail critical is 1.98. That means you have enough evidence to reject the null, and you can say, okay, there's a correlation. It happens to be a very strong correlation. That's the first row. The next one, even though you have a very strong correlation, you have such a small sample size, you don't quite have enough evidence to reject the null yet. Your t-statistic is 2, which is going to be less than 12.76. The t-critical is a lot higher because you only have 3 observations. You'll notice, like for the third row, the 2-tail t-critical value is exactly the same as the first one because we have 100 sample size of 100. It's the same. Your correlation coefficient is -1/2. And when you do these, you take the absolute value of it. And so with a -1/2, a sample size of 100, you end up with a t-statistic in order of magnitude of about 5.7, which is greater than 2 until you reject the null. And so with each of these, you want to look at what your t-statistic that you calculate, you compare it to the critical value. And if it's less than, you fail to reject the null. If it's greater than in order of magnitude, then you reject the null. And those are a few examples that we have with those. Okay, there's hypothesis testing. Let's talk a little bit about confidence intervals. Confidence interval is a range construed such that in a whole bunch of samples, the true parameter will be there X% of the time. And X% means 1 minus alpha. So if you have 5%, you're going to do 5% certainty. That means you're willing to be wrong 1 out of 20 times, but that's about it. And we've got the formula. I went online and I found some graphs that show some confidence intervals. That's the band. And each of these, it looks like, that looks like it's probably R. So the blue line or the middle one is the black line. That is the model. And then the range that you have above and below the plus or minus, that's the 95% confidence interval where you're looking at different things. And you would expect if you have, if you did, the confidence interval should be construed such that about 95% of the time you can anticipate the true parameter to be somewhere in there. A couple examples from an earlier class I have with with the and helping us understand how confidence intervals work. There's some statistics that are on here. Looking at a survey from US adults in 2017. People without health insurance at different levels of income, are they the same? Because we have the sample sizes were different. And so that gives us the range. And it looks like each of these three people they're not going to be the same for the first one. The second one, you're looking at US adults from 2016, from 2 different years, 18 to 25-year-olds. And we looked at different number of individuals. And if you were to calculate the confidence intervals, we have a 14.7%, the same as 16.6%. Well, because of the sample size, when you calculate the upper and lower confidence intervals, we can't quite say that these two groups are different from each other. Okay, yes, maybe the rate's gone up from 14.7% to 16.6%, but statistically, they're not different from each other. And that's an application of confidence intervals. Great, this concludes chapter 1. Please let me know if you have any questions.